Hey, lovely people! Welcome to your lesson on 1.11, identifying key features of linear and exponential graphs. So far in this unit, we have done domain and range, and then we have done where we have evaluated a function, where we've plugged in a value for the domain so that we could see what the values for the range were. Now we're going to look at linear graphs, which is a straight line, and exponential graphs, which is a curved line. And we're just going to identify key features of these graphs. We're not actually going to be making them quite yet. So, introduction. Real-world contexts that have two variables can be represented in a table or graphed on a coordinate plane. And there are many characteristics of functions and their graphs that can provide a really great deal of information. These characteristics can be analyzed, and the real-world context can then better be understood. So, key concepts. One of the first concepts or characteristics of a graph that we can observe are the intercepts. That's where a function crosses an x-axis or a y-axis. The y-intercept is the point at which the graph crosses the y-axis and is written as 0, y. So again, the y-intercept would always be, it would always have a value of 0 for x, and let's say 12 if the y-intercept was 12. And remember, when you have ordered pairs, always label them so you never confuse. X always comes first and then y. Just like in the alphabet, X, Y, Z. So when you're writing ordered pairs, X and then Y. The x-intercept, that's the point at which the graph crosses the x-axis, is always going to be your x value. So let's say 12, 0. We'll do the reverse, x, y. So here is an example. This one has the x-intercept. Remember your x-axis. Let me get the highlighter tool because I think this will be much better. This is your x-axis, and you see that right there, that's where the line crosses the x-axis. So that's called the x-intercept. It intercepts the x-axis at point, see it pretty little, 40, okay? 0.40. For the x-intercept, your y value is always going to be 0 because y is, let me get another color, right there, the y value is 0 at any point along the x-axis, okay? Let's look at the other graph. The other graph, we're looking at the y-axis right here. The y-axis is the axis that goes up and down, and any point along the y-axis, your y-intercept is going to have x value of 0 because you're not moving left or right for any of these. So if you look, I'm going to use a red marker. If you look right here, if we were to move left or right, we would no longer be on the y-axis. We would no longer have an x-intercept 0. All right, let's look at another one. Let's pull up the highlighter again, and we've got the left graph. We're looking for the x-intercept is 2, 0, 2, 0. It's right here. X-intercept is the one that crosses your x-axis, and it crosses at 0.2. That's your x value for a 0.2. I mean for 2. Again, let me label this to make sure. Let's use purple. That looks fun. Your x-axis and your y-axis. X-axis on this right-hand graph, your y. You can label them everywhere if you would like. There we go, okay? So we've got x value and we have y values for both x-intercepts and both y-intercepts. But if we remember, let's pull the highlighter tool back up again. If we remember, the y-intercept does not have a value for x ever. It'll never have a value for x because it's on that line. It's not left or right of the line. That means x is always going to be 0. And before we move on, I want to point something out. This is very, very simple, what I'm about to point out, and it's always one question on the EOC, okay? Your graph, you've been used to graphing things just with a right angle. So let me pull up, erase all the ink, and then you're used to graphing just in this quadrant from up until now, all right? So now you see that there are 4 quadrants of the graph. There's 4 different sections of your graph. I want you to sketch this out on your notes, okay? Just draw this box with the plus sign. You don't need to actually sketch the graph out, just a blank box with the plus sign. And inside of it, I want you to write down the quadrants of the graph, and I'm going to use purple. This is quadrant 1. This is where all your numbers are positive x's and positive y values. We are going to move to the left. The next one is quadrant 2. You have negative x values, but you still have positive y values because we are above the y axis. I mean, we are above the x axis rather. If we're above it, then we're going to have positive, but remember, if we go left, we have negative. Okay, we're going to keep going down. This, you guessed it, is quadrant number 3, and your values for x are going to be negative because they're below, they're down below. Your values for y are also going to be negative. So your values for x are negative because they're left, and your y are negative because they're down. And this last quadrant is 4, quadrant number 4, where you're going to have positive x values because they're to the right, and you're going to have negative y values because it's down. So again, quadrant 1, quadrant 2, quadrant 3, and quadrant 4. Okay, easy, but just remember that 1 starts in the top right and you go to the left all the way around. All right, another characteristic of graphs that we can observe is whether the graph represents a function that is increasing or decreasing. So when determining whether your intervals are increasing or decreasing, focus just on your y values. Begin by reading the graph from left to right and notice what happens to the graphed line. If the line goes up from left to right, then the function's increasing. If the line goes down from left to right, then it's decreasing. Pretty easy. So a function is said to be constant if the graphed line is horizontal. It's neither rising nor falling. So right here we have a function that is going up from left to right. It's increasing. And this function is going down. It is decreasing. And these are both increasing and decreasing at constant rates. Okay, let's look at another one. This graph right here, it is increasing and this is decreasing. Are these constant though? They are not linear. These would be exponential graphs, and they are not increasing or decreasing at a constant rate at all, hence the curved line. Okay, so an interval is a continuous series of values. So on a graph, if you looked at a graph of years, you were looking at a change in growth over years. Your years are your continuous series of values. So you might have it in five-year intervals or 10-year intervals. Continuous means having no breaks. So a function is positive on an interval if the y values are greater than 0 for all x values in that interval. And we'll look at what that means in just a second. A function is positive when its graph is above the x-axis, like we just looked at the quadrants. So anytime you're in quadrant 1 or 2, the function's positive. Begin by looking for the x-intercepts of the function. Write the x values that are greater than 0 using inequality notation. A function's negative on an interval if the y values are less than 0 or if it's below the x-axis. So if it's in quadrant 3 or 4, it's a negative function. So let's look at this left-hand graph. The function is positive when x is greater than 4. So you have x, this part, the function is positive when x is greater than 4. The function is negative when x is less than 4. So we're using x is less than 4 to represent this one, and x is greater than 4 to represent this one, because you look at where the function hits your intercept, your x-intercept. All right, now let's look at an exponential function. The function's positive when x is greater than 2. So right here, when x is greater than 2, and it's negative when x is less than 2. It's in our negative quadrants. Negative quadrants meaning quadrant 3 and 4. Okay, so graphs may contain something called an extrema, or a minimum or maximum points. A relative minimum is the point that it's its lowest, or y value is the least, or the relative maximum is when it's its highest, or the y value is greatest. So both linear and exponential functions will only have a relative minimum or maximum if the domain is restricted. That means if the graph doesn't go on forever. The graph on the right is of the same function, but the domain is for x is greater than or equal to 1. The minimum of the function is negative c, something more like this. We would not expect to see this for a real life situation that had anything to do with the cost of something, because there's not a negative cost. So there's several different ways to classify numbers. The following slide lists the most commonly used classifications when defining domain. These are a review from several different years. First, we've got natural numbers, numbers like 1, 2, 3. We have whole numbers, which include 0. We have integers, which are the negative numbers and positive numbers. We have rational numbers. We have irrational numbers, and rational numbers. You guys spent a lot of time in 8th grade with, and some of our works will go into rational and irrational. So irrational is any number that cannot be written as a decimal that ends or repeats, and rationals are numbers that can be written as a decimal that end or repeat. And real numbers are the sets of all rational and irrational numbers. Common errors: believing that exponential functions will eventually touch or intersect an asymptote. Asymptotes, I'll show you what that is in just a second, but it's something that you'll really get into in math too. For this class, we're just going to know what it is, and that's it. Incorrectly identifying the type of function as either exponential or linear, and misidentifying key features on a graph, and incorrectly choosing the domain for a function. Okay, goes on forever, no maximum. That's our minimum, it's the lowest point. And identify the domain. The domain can be written for this one as x is greater than or equal to 0. So the lowest x value is 0, and it increases infinitely. So because it increases infinitely, we can say safely that x is greater than or equal to 0. And identify any asymptotes of the graphed function. An asymptote is a line that a curved line approaches as it heads towards infinity. So the graphs here, we have these curved lines. They do not actually touch either axis. Because they don't touch either axis, they're never going to intersect the axis. It's going to just keep going on and on and on and on and on forever, infinity. The asymptote is that imaginary line that is just under the axis. And there's mathematical formula to figure out what asymptotes, like what the actual numbers of asymptotes are. And you guys will be doing that in math too. Value that is 0 down here, you don't have that. There is no y-intercept. Determine whether the function's increasing or decreasing. So we just saw that the y values were going up each time, and the x values were going down. The function is decreasing. Values for y are all positive, and for all x values greater than 0. So this function is positive. This function is never going to be negative. So if it were graphed, it would also be first quadrant. Determine the relative minimum and maximum of the function. So the data in the table do not change at a constant rate. Therefore, the function is not linear. So based on the information that we're given, this is exponential. Exponential functions don't have a relative minimum because the graph continues to become infinitely smaller. Height of the pendulum never goes higher than its initial height. Therefore, the relative maximum is your 0, 80. The lowest x value is 0 and it increases infinitely. It can be any real number greater than or equal to 0, but cannot be a partial swing. So the domain is all whole numbers. There's in your examples, the next number 7 is about the asymptotes. We are not going to be doing those this class. We will be doing those in Math 2. Have a great rest of your day.